Uh, in this video discussion, we will explore improvements made to the classifier, how its fate was accessed and enhanced, and the presence of a functioning classifier for stroke prediction, and the validation strategies employed to ensure reliable results. First, we want to talk about the enhancements to classifier performance to improve the classifier predictive capability. Several pre-processing, balancing, and optimization techniques were applied. First, we use feature engineering and pre-processing data pre-processing. We handle missing values by simple imputer and categorical features were encoded using label encoder and one-hot encoder. And for the numerical features, they were standardized using standard scaler. And feature selection was performed in the notebook by using select from model to remove redundant or less significant variables. And we also handling the imbalance data. Given the class imbalance in stroke prediction, synthetic minority oversampling technique, aka SMOT, was used to generate synthetic samples for the minority class. And this ensured for the model effectively learn from both positive and negative stroke cases. And thirdly, we also run model selection and hyperparameter tuning. Several machine learning models were implemented, including logistic regression, random forest, gradient boosting, SVM, and XGB boost. And Grid search CV was utilized to fine-tune hyperparameters and improve model performance. We also use ensemble learning. Like we use a voting classifier was employed. We use a voting classifier to combine multiple base models, leveraging the strengths of each to enhance predict power. And second part is we assess and improve the model fit. And to evaluate the classifier's effectiveness, multiple validation and performance assessment techniques were implemented. First, we use cross-validation. Stratified k-fold cross-validation was used in the notebook to divide the dataset into multiple folds, while maintaining the original class distribution. And cross-value score was applied to evaluate generalization performance across different data splits. Performance metrics in this part, accuracy score and ROC score were calculated to measure predictive performance. And confusion metrics and classification report provided insights into precision, recall, and F1 score. Given the dataset imbalance, ROC score was particularly important in assessing the classifier abilities to differentiate between stroke and non-stroke cases. And for the presence of a functioning classifier, of course, a fully functional classifier for stroke prediction was developed. The notebook implements and compares various models, selecting the best performing one based on evaluation metrics, and the inclusion of some ensemble methods further enhances reliability and robustness. Validation strategy, several techniques were employed to validate and refine the classifier. First, stratified k-fold cross-validation, like we talked about in the second part, it ensures that performance evaluation remained consistent across different subsets of the data. And also grid search CV was used for hyperparameter tuning and optimizing model parameters to prevent overfitting. As mode addressed the class imbalance, improving recall for stroke cases and enhancing model fairness. And feature selection techniques helped in reducing noise, ensuring that only the most relevant features were used in training. And in conclusion, this approach effectively improves the classifier's predictive performance, ensuring robust validation and optimizes feature selection and model tuning. The applied strategies contribute to a well-balanced generalized model for stroke prediction.